Hey dudes, we're checking out the new section of 3.1 Functions and Notation. This is from quadratics, but it's a great little warm-up, so pause me and try this. Find the value of k for which this has two repeated roots. Pause. Okay, so this is our a value, this is our b value, and if you subtract 1 from both sides, set it equal to 0, -1 is our c value. Right? Clean it up so it's in standard form. Then if it has two repeated roots, the discriminant, b squared minus 4ac, should be 0. And so b squared is k plus 3 squared minus 4, a is a k, and c is -1. So if we multiply all of this by -1, it'll change the sign on that. So you get something like that. When you expand this, you get k plus 3, you get k squared, plus this is 6k, and then there's 4k there, so you get 10k, and you get 9 equals 0. When we factor that, you get k and a 9, and a k and a 1, k and a 1, and you end up with k is -9, or k is 1, -1, sorry. Cool? Great. All right, moving on. We're talking about relations and functions and function notation in this set. And a relation is any connection with two variables. Sometimes we can write an equation for that connection, like this. We're looking at this equation. This is x plus 3. I always know that the y value is 3 more than the x value. Right, so if the x value is 0, this is 3 more. If it's 1, this is 1, 2, 3 more, so 4, etc., etc. So this is predictable. This is called a function, and we'll talk about why that's a function. This is still a relation. I can tell this is another way to talk about this is y equals square root of x. This is we can write an equation and such, but this is not a function. This is not a function, non-functional. We'll talk about why that's true. Some things we can't define as an equation, some relations, right? Some relations are just like, I want all of the areas, I want all the points that have both positive x and y values. So that's all of this. Sometimes you can't write an equation for them. Makes them relations, maybe not necessarily functions. So this is what makes a function. You should probably jot this down. Functions are relations where one input corresponds to only one output. Write that down, I'll give you a couple examples. Here's a relation. This is a relation. If you have friends, right? A relation, you have friends, you're relating to your friends. Amy, it's okay if Amy is friends with Brett and Steve and Laura. That's fine, right? That's no problem. You can be friends with many people. And it's okay, it's fine to have Daphne be friends with Laura and Steve and Philip. Poor Bart, nobody likes Bart. That's fine, right? That's a relation. But here, one person has 3 different outputs. So this is a relation that's not a function, because Amy can be friends with a lot of people, and it's okay, right? This is not a function, right? So this is non-functional. It's not a function, because one person has multiple outcomes. This is a function. It's also a relation, but it's a relation that works in this specific way, where one input has only one output. If you think about like your biological mother, right? Amy can have a biological mother of Laura. That's fine, right? And I only have one girl in there. How do I only have one girl? Let's see. Betty, Betty, right? And so somebody else could have like Greg could have a mom of Betty. That's fine, right? And Greg's not going to also have a mother of Laura, because if we're talking about biological parents, I know, we're just trying to keep it easy. There's only one mother for that, right? But it would be okay. It's just fine to have Daphne also have Betty as a mom, right? That means Greg and Daphne are siblings. That's not a big deal, right? So one input, one unique output to that person, right? So if you know this Amy, you can know exactly that she has one parent, right? Here's some other examples. Here's some functions. Your height based on your age. So if you were graphing this and you look at people's heights as they age, their years, right? Let's call this age. And this is their height. If you looked at babies, they're very small, and you get taller and taller and taller, and at some point, provided you do live long enough, your spine compresses, you actually get kind of shorter. So if you know, based on age, if you know somebody's age, their age should have a predicted height. Age should have a predicted height. Age should have a predicted height, right? That's fine. So if I looked at your age as I said, oh, you're 17, you go over to the 17-year-old category and say, oh, on average, 17-year-olds are this high. That's a function, right? One age, one height recommendation. But so that's fine. If you worked it backwards, if you said, let's draw another graph, this one, if you wanted not a function, if you did age based on height, if we put height here and age, it would look something like this. Let's see, the 0 age, low height, it would do this, right? So if you know that somebody is this tall, is whatever, 142 centimeters tall, they could be an adolescent, or they could be somebody who's old and has just had their spine compressed a little bit. So this one height has two possible ages they could be. Just like this height here, here, and here has two possible ages they could be. I know we're getting used to it, so we'll keep giving you some other examples. Here's another example. Boats going through the Panama Canal have to pay to go through, have to pay to transit, and the cost that they pay is based on their displacement, like how much the boat weighs. So when we went through the Panama Canal, there's my boat, it's right in the middle, and that's the front of my boat. When we went through the Panama Canal, they measure your boat and they tell you how much you have to pay based on mass. And so the mass of your boat and the cost has a predictable connection. If your mass is a certain amount, you should expect a certain cost. If it costs my boat a certain amount, right? If they said, oh, it works like this, except yours costs more, if they had like two different relationships for the cost, I would want this one and not this one, right? I want one mass. My boat was 8 tons, right? So I want an 8-ton boat to only have one cost to go through, not two costs and then somebody else picks. Why would there be two costs, right? We want one value, one displacement to have only one cost. And so that's this again, right? 1x corresponds to only 1y. Let's give you some mathematical examples. So every function is a relation, but not every relation is a function. That's fine. It just means that there are a lot of connections between numbers, but not all of them give you a 1-to-1 ratio. Let me give you an example with this. You can read fine print if you'd like. If you graphed y equals x squared, you'd get this. If you took square root of 1, you'd get positive 1 and negative 1, right? Because the square root of, square root. Square root of 1 is 1 or negative 1. If you did square root of 2, let's go 4, you'd get plus or minus 2. So if you went out 1, 2, 3, 4, your square root would be plus or minus 2. Right, so you'd be there, and if you went over 9, 9, your square root would be plus or minus 3, right? So your function looks like that, and that, or your graph looks like that and that. It's non-functional because it's a relation. There's a relationship between these numbers, but it's not a function because at 4, I put in 4 and I get 2 possible values out, and mathematicians don't like that. Yeah, we say it can be graphed. We can write an equation for it, but it doesn't behave in that specific way, which is this: one x in, only one output specific to it. Yeah. We can often use the vertical line test for this, where if you drop a vertical line, one x has 2 y's, and that's non-functional. So that's all that this is saying. Let me move this out of the way. If you can drop a vertical line and hit the graph once, like that, it means one x corresponds to only one y value. If there's any place that you can drop a vertical line and hit the graph twice, you don't have a function. So it can be wiggly as it wants to be, but as long as you have one intersection with a vertical line, you're golden. All right, so let's get some numbers in here. I think about functions as a machine, and that helps sort of illustrate this. So if we put in an x, we expect the machine to do something specific with it. So this machine does 2x plus 3. So if we put in a 5, it should go 2 times 5, 10 plus 3, so out should come 13. Yeah? If we put in a 5 and you get out of 13, you put in a 5, you get out of 13, you put in a 5, you get out of 13, you put in a 5 and you get out of 12, your machine's broken and it no longer is functioning, right? So we need to have one input give you only one output. Yeah, we're used to writing that as y equals 2x plus 3. We're going to start to write that as f of x equals 2x plus 3, which means into the function I put some x values, it doubles my x values and adds 3. Yeah. So for instance, if you were looking for what happens to your 5 when you go put it in there, you'd say, what's f of 5, right? This is not a multiplication. It's not f times x. It's f of x. It's an operation. Into the function, I'm putting x. Into the function, I'm putting 5, which means you're putting 5 in place of the x, adding 3. Sorry about my handwriting with a mouse. And you get 10 plus 3, 13, right? And so we can say f of 5 is 13. This is kind of nice because we have a coordinate right here. I put this x in, I got this y value out essentially. So 5, 13 is going to be on the graph of this equation. Yeah? What do I have hidden over here? Oh, stuff. Who knows? So this is the idea with functions, like one output is paired with each input. So if you put in cookies into your oven, it should make you cookies when what comes out, right? If you put cookies into your oven and you get 2 different things out, that's bad, right? So we think about these as function machines that are doing the same thing over and over again, and you only get one value out. So therefore, like when you get this square root of x, if let's put that down here, and let's put right 3x plus 1. If you put a 6 in here, you're always going to get out 3 times 6, 18. You're always going to get 19 out. But if you put a 9 in this one, you take the square root of 9, 3 can come out, but also negative 3 can come out, and that makes it non-functional, right? It doesn't behave like a machine. We want a machine to do the same thing every time. Boom, 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 boom. Cool? So it's kind of like, what's the difference between relations and functions? It's all about behavior, man. These are both aquatic fish or aquatic animals that swim and kind of look alike. What's their differences? These are friendly and play with safety buoys, and these will chew your arms off. And understanding their behavior lets you know how to predict things. So let's do some prediction. This is some ways to represent functions. This is called function notation using f of x. So we could say f of x is 2x, and here's the graph of 2x. It's the exact same thing as graphing y equals 2x, but we like to write it like this so people reading the work can understand how it's going to behave. I know one input gives you only one output. I know if I put 3 into this, it'll go 3 times 2. This is f of 3 is 2 times 3 is going to give me 6 always and only, right? 3, 6. That points on the graph. So we can represent these with some different in different ways. One of which is a ordered pair set, which is just the x's and y's. So you could write them out as like with an equation. You could write them out with a table. You could write a graph. You could make this mapping set. So what's the equation for this? It doesn't look like an equation. It's just bouncing around. But if they said, here's some relation, can you represent it in different ways? Here's -2, 2, -2, -2, da, da, da. We can make a table out of it, right? This is this. We could graph it. Here's -2, -2. And then here's -2 mapping to 2. So -2, it goes in, 2 comes out, right? It's okay sometimes, you can have a function with 2 of the same outputs. For example, f of x equals 0x plus 5. If you put, here's the x's, here's the y's, or f of x's. If you put in 1, you go 1 times 0 plus 5, 5. If you put in 6, you go 6 times 0, 0 plus 5. If you put in a billion, you put in a billion times 0 plus 5 is 5. These all have the same output, and that's okay, that's fine. But I know that if I put in 1, I'll always get 5. 1 goes in, 5 comes out. 1 goes in, 5 comes out. 1 goes in, always, always, always. Same for 6. It's okay that they're the same. And you would map that like this. 1, 6, a billion, right? There's the map for this. 5's the map for that. And you can just say, hey, all of them map to 5. Still a machine, still functioning like a machine. I always put in 1, I always get out a 5. Put in 6, I'll always get out 5. Billion, always get out 5. That's fine, right? So it's okay that this can point at, 2 different numbers can point at one of these. That's okay. But what you can't do is have a 9 go in and give you sometimes 3 and sometimes -3, right? That's non-functional. I want to put in a 9 and only get out 1. That's, again, the square root function. Cool? All right. Maybe you want to try this same thing without me talking at you. So here's a set of ordered pairs. Let's try to make them larger so you can see. Try to organize them in a table, maybe a graph, plot them on a graph, maybe mapping. Pause me until that. All right, so with the table, table set would look like this. You'd put your x's on one side and say, oh, the 0 gives me a 2, the 1 gives me a 3, etc., etc. For the graphing, you just plot the points. What's that there? Plot the points. Boom, boom, boom. This one happens to be in a line, which means I can probably write an equation for it. And if it's a function, then I can use the f of x notation. This looks like 2 plus 1x, or x plus 2, right? So that's a graph. Here's another way I can write it with function notation. This one, if I could write a graph for it, I would use y equals because it's not a function. Or I could write an equation for it. And then you can also do the mapping for it, which is fine. Cool? All right, so if we want to evaluate the functions, last but not least, evaluate means sort of like solve. So f of 3 means you put a 3 into the x. So this would become 2 times 3 into the function I want to put a 3. So put a 2 times 3 plus 5. So f of 3 is 15. Yeah, that's fine, no big deal. You can do the same thing into the function I'm putting k. So this becomes 2k plus 5. That simplifies to 2k plus 5. And this guy is f of m plus 2. So into the function, wherever you see an x, I'm going to put m plus 2. And so m plus 2 pops into here. you can distribute, so you get 2m plus 4, still plus 5, and you can simplify 2m plus 9. Cool? That's function notation, that's evaluating. Go and check out the function notations, go all the way up and stop at sign diagrams. Neat? Neat.